All right, so we are going to study the fundamental theorem of calculus with a fun scenario where Mr. Walker and Dr. Ricketts were creating this lesson in Mr. Walker's room last Friday after school. I exclaimed that something smelled funny to an oblivious Mr. Walker. We examined some student's forgotten backpack. I don't know who David is, just go with it. And we found a Tupperware container that had a half-eaten tuna fish sandwich covered with a huge growth of greenish mold. The smell was overpowering, and let me just tell you that tuna fish grosses me out beyond belief, so I was probably about to vomit. Mrs. Frizzle happened to be walking by, and upon seeing the mold, and by the way, I don't know who Mrs. Frizzle is either, just go with it. The bacteria population would have been increasing at an instantaneous rate of 200 plus 50 bacteria per minute, where time is measured in minutes. Mr. Walker instantly said, "Yippee! We can use this information to teach the fundamental theorem of calculus next class." And Dr. Ricketts was equally excited, and we both grabbed pencils and ran to scribble notes on a piece of paper. Mrs. Frizzle, who was well aware of the fact that both of us are a little loony, challenged us both to figure out how much the mold population had increased in the 8-minute time interval beginning 2 minutes after she arrived, i.e. on this interval from 2 to 10 minutes. When we were finished, Mrs. Frizzle declared that we both had the right answer, but strangely had worked out the problem in two completely different ways. So let's take a look at the two approaches. What Mr. Walker did was graphed the function 200 plus 50t on this grid at the right. So we have a y-intercept of 200, and then we have a slope of 50. So we go up 100 for every 2. We've got this nice linear equation here. I started it at time equals 0 because time is not negative. So here's my linear equation representing Mr. Walker's thoughts. And the units of the vertical axis are going to be in, it looks like, mold spores per minute. So this is, Mrs. Frizzle said that we have an instantaneous rate of 200 plus 50t bacteria per minute. So we're going to go with bacteria per minute on this y-axis here. So bacteria per minute. Now on the x-axis, the horizontal axis, we are going to have time, and that is going to be in minutes. So now if we want to evaluate f of 4, we just come over here and we get the number 400. So then they say, well, what does that mean in the real world? Well, what that means is that at time equals 4 minutes, and don't forget you need units, you need to state the time, the mold population is growing at a rate of 400 bacteria per minute. And we just read that value off of the graph. We could have also evaluated the equation at time equals 4. So then they say, okay, let's determine the integral of little f of our function from 2 to 10. So to integrate, what we're going to do is use our known geometric areas. And I have a trapezoid here on the interval from 2 to 10. And I know that my area of a trapezoid is going to be 1/2 times the height, and the height will be 10 minus 2, or 8, times base 1, which is the height here at 2, it looks to be 300, plus base 2, which is the height here at 10, which when I plug in 10, I get out 700. It's really up here. So 700 there. And then I calculate this. 300 plus 700 is 1,000. And 8 times 1/2 is 4, so I have 4,000. And of course I need units, so my units are going to be bacteria. I'm sure it's some sort of bacteria spores, but what I did was take bacteria per minute times minutes. And it looks like, my friends, I have just graphed the region. Now they want me to shade it. So if I shade this region, here it is. So you can get a feel for the representation of this. And they want us to tell them what this integral of f of t from 2 to 10 represents. Well, this represents the total change in the number of bacteria spores or something like that, number of bacteria on the interval from 2 to 10 minutes. All right, well, now let's take a look at what Dr. Ricketts did. What she did was she came up with a mysterious equation and called it big F of t, and she said it's equal to 25t squared plus 200t, and that it's valid on the interval from 0 to 10 minutes, where big F is the approximate number of bacteria, and t is the time passed since Mrs. Frizzle entered, and we already know it's in minutes. So on the grid right here, what we want to do is we're going to label the vertical axis population in bacteria or population of bacteria. And then my horizontal axis, I'm going to label as time. And this is going to be in minutes. So let's graph this equation. We know that we have a vertex here at the origin. And then I can just start plugging in values. If I plug in time equals 1, looks like I'm going to get 225. If I plug in time equals 2, it looks like I'm going to get 500. And I might skip to time equals 4. 16 times 25 is 400, plus 800 is 1200. And then I might skip all the way to 10 just to see how far up I go. 25 times 100 will be 2500, plus 200 times 10 is 2000. So 10 maps to 4500, which is up here. And since I know this is quadratic, I can just sketch a nice quadratic curve connecting the data points that I have on my grid. So find big F of 10. Well, that's this point here that I've already calculated. Big F of 10 is 4500. Well, since I'm reading off of the graph and the y-axis represents the population of bacteria, what I just found was the bacteria population at time equals 10. At time equals 10 minutes, I should say. So find big F of 2. Well, that's down here. When I plugged in 2, I got up 500. So that represents the bacteria population at time equals 2. And again, time equals 2 is 2 minutes. So now let's subtract. What's big F of 10 minus big F of 2? Well, that's 4,500 minus 500. So that's 4,000. So what is that in the real world? Well, that is the total change. Does that phrase ring a bell? Total change in bacteria on the interval 2 to 10 minutes. So then it says, okay, on the graph of big F, let's draw a line segment that represents big F of 10 minus big F of 2. Well, here's big F of 10 up here at 4,500. Big F of 2 was down here at 500. So what we have is a vertical line segment that represents the total change in the bacteria population. This is big F of 10 minus big F of 2. Now let's go ahead and differentiate Dr. Ricketts's big F function. Big F prime by the power rule is going to be 50t plus 200. And the units, instead of just bacteria, we're going to have bacteria per minute. So that should look familiar to you from the prior page and Mr. Walker's thoughts. So what we have found is that Mr. Walker's rate function is actually the derivative of Dr. Ricketts' function, big F, and by the same logic, the big F function that Dr. Ricketts used is actually an antiderivative. Notice I said an antiderivative because it is not the general antiderivative. It is a specific antiderivative of the given rate function, little f. And we know that the total change on little f from 2 to 10 was 4,000 bacteria. And we also know that the total change on big F from 2 to 10 is 4,000. So that means that we can set equal the integral of the rate function from 2 to 10 equal to the total change on the antiderivative function, the position function, also from 2 to 10. So that brings us to the point where we can conclude, which is the first part of the fundamental theorem of calculus. If you have little f, which represents a rate at which the function big F is changing, in other words, the derivative of big F is little f, then the integral of that rate function, the integral of little f, represents the total change in its antiderivative on a given interval. This right here, symbolically, is the fundamental theorem of calculus. The integral from a to b of little f of x dx is equal to big F of b minus big F of a, as long as big F is an antiderivative of little f. This, just so you know, is what I was referring to when I said you're going to see things in memes and on t-shirts and in movies or TV shows. You're going to see references to this in common media, and you're going to recognize it now. You never recognized it before, you just ignored it before. If it makes more sense to you, you can also write it like this, that the integral of g prime of t dt is equal to g of b minus g of a, as long as we integrate it on a to b. These are the same statements. The only difference is that we're using big F to be an antiderivative and little f to be the derivative, versus g and g prime, which might be more intuitive to you, that are a function and its derivative. In words, what we say is the definite integral of a function on the closed interval from a to b is equal to the total change in the antiderivative of f on the same interval. And notice we have these asterisks here. That indicates an especially important concept in this packet, and frankly in the course, because the fundamental theorem of calculus is the linchpin of the course that connects differential and integral calculus.